Hi, welcome to a Tenasia Group presentation on Make the Elephant Fly, how to make Hadoop 10 times faster in 10 minutes. I'm Mike Matchett, Senior Analyst with Tenasia Group. First, a little introduction of who we are. We're recognized IT industry analysts. We focus a lot on enterprise infrastructure. I personally do virtualization, storage, and big data in the nexus of those things. Overall, we do a lot on how data center is managed across virtualization cloud, all sorts of platforms, infrastructure operations, performance and optimization, particular specialties, and we certainly address all virtualization types. Now, we're a small company, but we believe we have a bigger impact because of our technology depth and our operational expertise. Our analysts are all vetted field and subject matter experts here. The net of this is you can come to us for emerging markets analysis, technology validation, and even end-user research. Okay, what are we doing today? First, I'm going to talk just a few minutes briefly about the big picture of big data and big Hadoop in theory and the problems with Hadoop when it gets into production. Mainly, we'll talk about some performance issues and where we bottleneck. And then we'll introduce this in-memory opportunity. How does one take advantage of memory in Hadoop? And doesn't that seem like a contradiction in approaches when you step back and look at what Hadoop was originally designed for? So we'll dig into that in a second. Then I'm going to spend a decent amount of time interviewing Nikita Ivanov, who's the founder and CTO of GridGain. GridGain has an in-memory solution which is very powerful and has recently extended that to include Hadoop. We'll talk with him for maybe 25, 30 minutes, and then we'll take some audience Q&A. And I'd encourage you in the audience to go ahead at any time and start entering questions when they occur to you under the tab on your Bright Talk screen, and when we get to that section, we'll try to answer as many as we can. Okay, so what does big data really mean? There's lots of definitions of big data, but for me, looking across all the different definitions, it's about getting value out of data that was previously unexploited because it was too something. It was too big, too fast, too detailed, too raw, meaning unstructured perhaps, not processed, and even too dynamic, that's changing too fast. And that meant that the data centers of our traditional IT were processing structured data that was able to be extracted, transformed, loaded into an RDBMS, and that limited its size and its scope and was a fairly expensive proposition. Now, if you look at this picture on the right here, this is actually a stellar map interpretation of the Internet showing all the different sites on the Internet, and it looks like a whole universe. And this is, in fact, what Google attempts to capture and search every day, and they tend to actually copy this whole thing down into their processing. And in fact, Google did a lot of research which became the genesis for the open source project and drove the implementations of what became Hadoop and inspired the folks to write Hadoop and HDFS. So this is a direct tie-in here. Now, what is Hadoop? Just briefly at a high level, it's a scale-out approach. We're going to tackle this new kinds of data at whatever scale, format, and structure they have by putting the data across a cluster of affordable machines. And we're going to do it cost-effectively. We're going to try to avoid our limitations and our expensive RDBMS BI constraints that we've had previously with traditional solutions. That's based on distributed processing. You probably heard of MapReduce. Now, MapReduce says I'm going to take my computational job. I'm going to break up into parallel pieces, and I'm going to farm them out across a cluster. And I'm going to let them each work on a piece of data that's local to that cluster. That's where the Hadoop distributed file system comes in. They go hand in hand here. You put your data into HDFS. It basically breaks it up and assigns it out across the cluster of nodes that are participating. And then it works with MapReduce when it's time to compute a job, and the particular job that needs to run says, I need this data, and it says, okay, that data is over on node X, and it sends it over there. Now, this is really interesting because it scales linearly with the amount of data. You add more nodes, you get more processing power, you get more data space, but it doesn't necessarily make it any faster in total. It is cost-effective to tackle jobs that couldn't be tackled before, because you're using commodity servers and local storage, but it doesn't necessarily give you any particular performance guarantee. It's really a batch job kind of environment, and to really take advantage of it required some low-level parallel programming at first, although that's gotten better with different versions. We're going to see that IT really wants to work at least a query level, if not a structured query level, and I'm sure that'll come back in our discussion. So that's in a nutshell what Hadoop is. Now, when you take Hadoop and you put it in production, as we saw, because it's really this batch-oriented way of farming jobs out and getting answers and reducing them back, it scales with cluster size, but the performance doesn't necessarily increase on it at any point, and you can take a long time to get any answers back. So it limits the kind of applications you can do on it. There's also some question of availability in Hadoop. There are some single points of failure. They've been variously addressed over versions, but still, when you're working across a cluster, the bigger the cluster gets, the more problems you can have with this, and there's definitely some issues with Hadoop at scale in terms of availability. There's also a question of analytical data consistency, because as you're adding data to the system, say the data is coming in very fast, and your batch job's taking hours to run, obviously you're going to be hours out of date with the latest data that came in. And we'll see that what a lot of folks have done is said, hey, I need a whole second system to handle what's coming in very fast. And Twitter and Facebook and folks have all implemented different things. I'm sure that we'll talk about that too, to handle this idea of how do I deal with fast data coming in and the bulky existing data I already have in one system. Also, there are some management challenges with working with Hadoop. There's a lot of moving parts, and it's a fairly large ecosystem. Now, as we saw, the key to the Hadoop enablement of big data was that it makes use of commodity disks, commodity hardware, commodity servers. But it doesn't really talk much about memory. And so what we're also seeing as IT analysts is that not only do we have non-volatile RAM like flash getting cheaper and coming to the data center, but we see things like memory getting denser, cheaper, more available, servers coming with more and more memory on them to take advantage of, to the point where we can start to talk about memory as a key resource for big data. And this is just a little graph of Moore's Law. Some people predict that Moore's Law is going to level out here soon, and then other people are predicting that there's going to be some new technologies that keep it going up. And so far, the ramp is still going up. So it's pretty impressive over the last 30, 40 years. Now, with enough memory, you might be able to take what current approaches to Hadoop and say, okay, I've got these batch jobs, but I can run them every day now over tremendous amounts of data and get answers out of it, and actually make them operational speed. Like, I have an interactive question I want to ask of that big data, and I want an answer now. Well, that creates a whole other class of applications. Or I've got data coming in, and I want an answer to process over that data that's coming in very fast, and not just the data that I captured 6 hours ago and past. And I'm sure this is going to provoke a lot of other thinking, and hopefully we'll have time to come around at the end of our discussion there. So, with enough of my babble at the top here, I'd like to introduce our guest today, Nikita Ivanov, founder and CTO of GridGain Systems. Welcome, Nikita.
Thank you, Mike.
Nikita has, you have over 20 years of experience in application development here, certainly all over the place in high-performance computing and middleware. And of course, being a founder of GridGain, an in-memory computing platform, right? So, really looking forward to giving you a lot of questions here, and hope you can help us shed some light on stuff. So, just to start, can you tell us a little bit about your background and why in-memory is so hot right now?
Yeah. So, I started long ago. I started like in the mid-90s, late 90s, working on distributed computing in a project called Globus. It's one of the first grid computing systems. And essentially over the last decade and a half, it kind of progressed through different stages. And we're today talking about, we're not talking about distributed computing as something special. That's becoming a norm today. But I literally started almost 20 years ago when it was not norm. It was fairly, scientific. Three-letter agencies use that, but today it's really become an everyday tool. And
so like high-performance computing technologies coming into the mainstream, you might say.
Yeah, exactly.
Okay.
And we started looking at working on it in-memory computing maybe about 7 to 8 years ago, and it was essentially a precursor to GridGain. software. And it really was interesting back then. It was a kind of interesting concept that, we kind of knew that, if you put data in memory away from disk, things will get a lot faster. The problem was always that, first of all, the amount of memory you can put on a single computer was very small, and then you have to string together many, many computers to get any sizable memory pool. And the price of memory was pretty high. And although we knew about in-memory computing, and there were some, sporadic uses, in financial services and spec applications in military and whatnot, in-memory computing never really took off in a big way up until probably 2 or 3 years ago. And the reasons for that are quite, I would say, obvious today. If you obviously, what you just said, Mike, in your introduction, that we had a massive influx of data growth in the last, let's say 5 years. It wasn't just a continuation, it was explosion of data growth, and therefore demand to process the data grew in the same way. What also happened, and that's what probably most people don't realize, is that the price of RAM has been on decline for the last 30 years. It's still a little bit more expensive than flash and disk, but essentially today, the price got to the point, not today, but in the last couple of years, we kind of reached the tipping point where the price of DRAM really stopped becoming an issue in systems. I can give you an example. The terabyte of RAM, a terabyte of RAM today costs roughly about $25K. $25,000 costs a terabyte of RAM. Let me give you a perspective. According to most of the analysts, the 90% of all businesses globally can fit the operational data sets into 2 terabytes. So essentially,
$50,000 worth of memory, we can basically put our whole operational database live in a memory data set.
Absolutely, yeah. Over 90% of the businesses globally can put the operational data sets into the hardware that costs about $50K. Now, $50K is still not a zero, but if you consider that memory gives you anywhere from 500 to 1 million times performance increase on the raw hardware performance, that's a staggering advancement. Just to give you another example, because this number is kind of big, it's always, they look a little bit kind of foolish when you just talk about the numbers. Let me give you a concrete example, just kind of round up this introduction. Recently closed a deal here at GridGain with, large financial company. It's one of the largest bank in Europe. But the real interesting numbers were there that we achieved a billion transactions per second on the 25,000 worth of hardware. Now think about this. It's nothing to do with GridGain. It just has to do with the promise of in-memory computing as a whole. You can get to this really astronomical numbers on performance side on a very, very modest amount of the hardware. Think about this. 1 billion financial asset transactions on just $25,000 worth of hardware. This is the numbers we all have to keep in mind when we talk about in-memory computing, and this naturally directly applies to the conversation we're having today about Hadoop.
All right. So obviously, GridGain, you've been doing this business, and we've been talking about in-memory databases and transactional-oriented solutions. Now, let's talk a little bit more specifically about Hadoop. Right? Why is before you tell us about how you tell us, why is the out of the box or out of the distro Hadoop really slow? What's the real bottlenecks there? First of all.
Well, Hadoop, what's interesting, I think you actually made a very fine observation in the introduction that Hadoop was never designed for speed. And it's sort of like, people who design Hadoop not up to snuff. They're very smart people. But Hadoop was never designed for speed. It was designed for cost reduction. That was the single number one purpose behind Hadoop, is to use commodity scale-out hardware to process the same data we've been processing, on a very expensive data warehouse systems. And so the performance was never a design issue or architectural goal of Hadoop. So the short answer is Hadoop was never designed for it. And, historically, a lot of people jumped on it, initially. And, as you probably remember, initially there was a lot of confusion about what Hadoop is and what can do, what cannot do. And a lot of people jump on it, start storing data in it, and eventually start basically trying to do processing, and quickly came to a realization that, oh my God, it actually can take days, sometimes a week to process something, let alone forget about hours and minutes.
Right. The realization was, here's stuff I couldn't process before. Now I can process it, but it still takes days. It's doable, but it takes days. And lots of people have ideas that say, I want to process huge amounts of data, but get answers in minutes or seconds even, right?
Yeah.
That's what we're talking about here when we can get this kind of performance boost. So you mentioned a few customer examples, and have you done actually any testing with Hadoop? What can you do for Hadoop?
Yes, we actually, well, specifically for us, we recently released this, what we call the in-memory accelerator for Hadoop, and we have a number of customer trials going right now. There's multiple approaches here when it comes to accelerating Hadoop, and one of them, for example, is what we do in GridGain. Another one is the Apache Spark, which is another interesting approach to do this, achieve the similar goals with the different means. What we do specifically here is that, well, if you know anything about a Hadoop architecture, it's essentially based on two core technologies. One is HDFS, which is the file system, and that's the means how do you store all this information in distributed fashion. So essentially, it's a distributed file system that is based on disk. It essentially stores files on disk of multiple computers. Another technology is a MapReduce, and that's the kind of a cornerstone for other languages on top of that. So MapReduce is essentially an API you can write to it, and then there's not many, but there's a couple of popular scripting languages like Pig and Hive that give you a little bit more kind of query language interface, and they compile back to MapReduce. So the HDFS and the MapReduce are two basically cornerstones for the Hadoop. One is a file system, another one is a processing framework that allows you to parallelize the processing. So essentially, the idea that we had a couple of years ago was around this. How can we speed it up? And the way you speed it up these two technologies. You somehow speed up HDFS, and somehow you speed up MapReduce. If you do both, hopefully get pretty good returns as far as performance. And that's exactly what we did. First, we developed a industry-first full in-memory file system. So essentially, we developed a HDFS compatible, 100% compatible, you can basically replace it completely, file system that stores data in memory across multiple computers instead of in disk across multiple computers. And the second thing we did, we redeveloped the MapReduce. Again, it's a fully compatible 100%, nothing you have to replace or change. And we redeveloped the MapReduce implementation to take advantage of the data that's stored in memory. So that's in a nutshell what we did. And we're showing some really incredible numbers. Literally with absolutely zero code changes, fully plug and play. It takes about 5-10 minutes to download and install it. You can get performance increase right out of the box anywhere from 2 to 10 times. And even on things like Hive and Pig, we're showing a significant performance increase from anywhere from 2 to 5 times as well.
All right, so I can get some pretty big multiples here, but you just went past something. It's plug and play. I mean, if I've got a Hadoop cluster, I can just download this and I don't have to really be changing too much.
You don't have to change anything. As long as you have, whatever memory you have in the system in the cluster, we can utilize that. There's no need to change any code. You need to change just a small configuration file to really introduce the GridGain Accelerator to it. But you don't have to recompile. You don't have to change code, nothing at all. Okay. It's all based on this new Hadoop architecture called Yarn, kind of Hadoop 2.0, right, that has this pluggable support for multiple MapReduce implementations. We're just one of them.
All right. And does somebody have to decide what goes in memory or what stays on disk?
Yes, you have a full control, basically. You can decide which files, either all of them, for example, from HDFS go to memory. We have a lot of, interesting optimizations where we can pick the most active files and move them automatically in memory. Or you can basically dedicate a specific folder on your file system and say, this folder goes in memory because I'm constantly using these files in this folder, and therefore I want to be fast. So there's a plenty of,
Right. No, it sounds like on one hand you're able to sort of automatically cache what's hot, and then on the other hand you can make an in-memory storage repository or storage tier out of it.
Yeah, user selection is important here because look, we're talking about now historical data sets. And obviously, we're not expecting that everybody will, somehow acquire petabytes of memory and move everything into the memory. So the use case where you move everything automatically in memory is rather impractical if you have a large Hadoop installation. So we're giving you the ability to say, look, most of my data, I will never touch it, which is, by the way, sad reality in Hadoop systems. 90% of it will never be touched. It's just the storing for the sake of storing it. But I do know, for example, that this, last week of logs, for example, or something like this, I want to really keep it, fast. So you can configure that to be in memory and then have much better performance on this.
Okay. So, yeah, okay. So we've got now you said anywhere from 2x, 5x, 10x. You threw out a couple different numbers there. I assume this is workload, sort of workload dependent. But folks can try it on there. And I know, and you didn't mention yet, but this isn't necessarily something people have to buy to try, right? There's open source here.
Yeah, it's completely open source. As a matter of fact, we're moving even further. We're becoming part of the Apache Software Foundation, but currently it's software is Apache 2.0 license, so it's completely free, frictionless to try. We're open source company. We have open source project. We have a commercial version as well for those folks that need commercial features and support and everything else. But it's a completely frictionless to try.
All right. So here's a more difficult question. So, what are there any alternatives to in-memory computing for accelerating MapReduce jobs? And as you're looking at those alternatives, do they really overcome the main obstacles that we're looking at?
Well, there's multiple projects in this area. We're one of them. Apache Spark, as I mentioned to you, is another one. And this is a very interesting project as well, but it requires complete rewrite of Hadoop application. When it comes to just alternatives to MapReduce, to the memory computing, hardly any. There's definitely a kind of stopgap, approach to basically move to Flash. But Flash is nothing more than a faster disk. There's nothing more than that. You still have this whole chain of, events that happens from application to operating system, I/O control, and then device. And what Flash fixes is the device seek time. So yes, Flash is, about 30 times faster than disk when the seek time comes for actual device. But then you have the entire, chain of events all the way back from marshalling, demarshalling, from device to I/O control to operating system application. So Flash really doesn't bring much of an advantage. Facebook did a very big study a couple of years ago, maybe a year and a half ago, where they have one of the largest cluster in the industry when it comes to Hadoop, and they put some of it on the Flash, and then they introduced some of the caching in memory, essentially technology into the HDFS. And the conclusion was pretty clear that Flash doesn't really bring anything to the table. It's a very marginal increase in very specific use cases. Caching, on the other hand, really did provide an increase. It was a visible, sizable increase in a Facebook installation. And it's very natural because if you think about the numbers, if you think about the performance difference and architectural differences when it comes to memory, because in memory is not only about just a raw speed. Yes, of course, memory is faster than everything else today, but it's, the fact that data resides in exactly the same address space as your code brings a lot of different optimization that you can do. It's a very distribution friendly because, you can basically move only code. You don't move data. Data stays on distributed computing. You only move code, and code is a lot smaller. You'll be surprised. We're talking about, bytes, not even kilobytes most of the time. And the code doesn't change as frequently. So there's a lot of architectural advantages that you can take, you can implement when you talk about in-memory computing. And again, Flash is really just a faster spinning disk. There's nothing more to it. So I don't think, to answer your question, kind of as underlining, I don't think there's any much, different approach rather than in-memory to really speed up the Hadoop installations.
Yeah, I know, and I guess coming from a heavy storage background here, we tend to see people saying, hey, if it's an I/O problem, we'll just get faster storage arrays and even go back to some enterprise external storage arrays, and that just seems like a very expensive proposition that can't possibly give you the returns that doing this can in terms of performance.
Yeah, we've had several clients, that in several kind of use cases where people went this route and then network saturates, and then it's almost a never-ending problem. You fix the network, then you have to fix storage, and then you fix the application. So it's And when it comes to just replacing storage with the fastest storage, it's almost zero-sum game. You lose somewhere, you gain somewhere.
Yeah.
Within memory is a really kind of breakthrough. It's one of these, unique situation where if you can't take advantage of that, that gives you a net plus, a significant plus. You gain a dramatic performance advantage that's simply unattainable in any other way right now.
Right. And some of the reasons I might go to external storage, people talk about making sure I have the good right data protection, make sure I have the availability. But when we talk about GridGain and its in-memory platform, that also increases some of those resiliency availability factors too, doesn't it?
Of course, yes. We actually have. Surprisingly, you mentioned, we have a number of interesting use cases and customers, I think, where they specifically use in-memory systems because they want to keep a certain amount of data just in memory and never touch the disk. Because as you know, when you touch the disk, it's forever there. Even if you erase the disk, it's still recoverable. You have to really go physical destruction to remove data from the disk, and that's a big security and privacy problem. When things in memory, and you keep them in memory only, specific data, for example, very specific, subset of your data. You can be guaranteed that whenever you power it down, this thing is gone and it's not recoverable. And this kind of interesting property is really used by quite a few folks to really have a high secure environment, that is transient. And that's an interesting use case. I agree. So in-memory computing is at least the same secure as the disk-based, but in many situations it can provide a very unique security profile where you can really take advantage of that and have a better systems from a security perspective.
Awesome. Okay, so are there any, when people go to adopt, I guess let's keep on adoption just for another second. When people go to adopt this, do they run into any other obstacles? I mean, maybe even some business-related things, or is it pretty much just a technical implementation?
That's a good question. We probably can split it in two. I think there's a question about overall in-memory computing adoption, and a question about specifically to us about our Accelerator adoption. So answering the first question about overall kind of in-memory adoption, I think there's definitely a certain barrier to hop over because it's a very new concept, and most of the time it's not like you can just turn the switch on and off. Even in some simplistic use cases like database options, like in Oracle, it still requires significant rework on database layer for users. But when it comes to our specific Hadoop accelerator, that's what we basically try to solve, and that's why I was keep repeating this word plug and play. We kind of anticipated this problem that people, spend so much time with Hadoop already that they don't want to tinkle it again. They don't want to rewrite anything. They don't want to change much. So our Hadoop accelerator is completely plug and play, and that's a very unique feature of that. So adoption for that particular product for ours is very minimal. You download it; it's free. You download it, you install it, and you see it for yourself. See what kind of numbers you can get. Talk to us; we can help you out with some of the configuration issues and some of the ideas we've seen. But it is very simple, and you can very quickly ascertain whether it helps you or not. Because it doesn't help in all cases, and that's one of the problems with Hadoop, because some of the payloads can be so skewed in a certain direction, for example, being very much IO intensive or being very much computational intensive, that in memory may not help you much. It may give you 20, maybe 3 times advantage, but not 10. So it's always good to know. It's always good to try it out and see it for yourself, and that's very simple.
Right, but then you can remove this just as easily as well. It doesn't install itself and make itself a pain to get out of there.
No. It's a simple installation. It installs, just literally side by side with Hadoop. If it doesn't work for you, it's 1 second to remove it.
All right. Yeah. So I mean, that sounds really low risk. And is managing it over time and monitoring it get more complex? In-memory database grid sounds intimidating to folks.
It does sound this way, and we ship with our commercial enterprise version. We ship very sophisticated DevOps suite that gives you all the deep insights into the system and how it's running in a distributed fashion. So yes, we support that. Even an open source edition, I think right now includes that in limited fashion. But I think Hadoop ecosystem right now is getting to the point where it's fairly mature from operation, from DevOps standpoint. So yes, it's always the issue. When you're running, 10, 15, 20 computers in a cluster, it's never, walk in the park. You got to do something to monitor that and understand what's happening in the system. So I don't think that in-memory computing or GridGain specifically adds much complexity to this picture. Picture is already fairly complex.
And we know the Hadoop ecosystem is working on management solutions, and it sounds like you guys fit right into that. Now, you mentioned something earlier about Spark. You mentioned a couple times being a secondary kind of a different approach, and I think it's worth repeating. So if someone has some of these issues with performance, they might be looking at Spark. It's obviously a talk there, but Spark does require going to a different language, writing different applications, really duplicating a lot of effort, doesn't it?
Yeah, Spark, first of all, it's a great project. I like it a lot. But they take a different approach. They took a different approach. The goal is pretty much the same. It's basically somehow provide this, fast in-memory, big data processing, if you will. But their approach is, pretty straightforward. They essentially say, look, you have a Hadoop, throw it away. Just, we can load data from Hadoop, but for us, it's a completely different ecosystem. It's in different APIs, different new languages. It's the whole new ecosystem. So the only connection to Hadoop there is that we can load data from Hadoop into the Spark. And once you load it to the Spark, you have to rewrite your applications to really do the Spark way. And Spark way is very elegant, and I like that. But that's a fairly big hurdle. And there's plenty of organizations that will take this route, but there's probably even bigger type, group of organizations that cannot take this route yet, because they invested so much in Hadoop and they like Hadoop way. And for them, GridGain Accelerator provides this option where you don't have to change anything.
It sounds like even if you were going to adopt Spark for whatever reason, you still could implement GridGain on your Hadoop applications and speed them up by 10x anyway.
That's what we're seeing across our kind of user base, is that there is definitely sentiment both ways. None of them are exclusive, and none of them are wrong. It's just whatever fits your organization, your immediate plans.
Yeah, is there any real reasons? Other than you might only get 2x performance, are there any real reasons you wouldn't want to implement in-memory in Hadoop right now?
It's a good question. You're obviously asking a very biased person. So if I put my GridGain hat on me and say, I would say you're going to be nuts not doing this, right?
Right.
But there's many business use cases where people basically kind of adapt the business process to be kind of overnight and be slow, and they may not have immediate need for this. But I'm probably biased because most of the customers we've seen at GridGain, obviously, they come into us with a problem. Things are slow. It takes hours, we need seconds. How do we fix that? So we're not seeing those people who basically, satisfied with the current performance.
All right. Well, I had to ask you a tough question. All right. So looking forward a little bit, right? I thought about this a little bit working with you guys. But just in your sort of picture, what are some of the new workloads that you're going to be able to do with this? What are the new ways of thinking people should think about Hadoop? I know you guys even have some stuff coming out going up to Hive now. But in general, and then we can get specific, what kind of new workloads should people be thinking about tackling if they can accelerate Hadoop 10x?
Well, I think the biggest one, and I don't want to sound kind of too academic here or too prognosticizing, for the next 10 years. But the payload we're seeing is the more and more operational payloads moving to Hadoop with technology like GridGain. Because before that, it was almost, inconceivable. There's no way you can run business with something that takes minutes and hours processing anything. And therefore, Hadoop was moved quickly into the kind of back office batch-oriented processing, for this, data sciences that can take weeks and months to munch the data and get some insights. So we kind of, chewed up this problem. That's done already, and businesses, most of the time understand how to do it. But they're starting to look, okay, so we deploy this Hadoop cluster. We keep most of our data there, or some of the data there. Can we not use it somehow for actually running the business, to make decisions in real time, to run our website off of it, to improve, scoring, to improve modeling, to improve user experience, and all these different things. And that's where basically, that's actually what drove development of Spark and GridGain Accelerator. And that's in return what's going to be enabling, what we're going to be enabling to, is to really inject Hadoop-based systems into the operational workflow of businesses. So if Hadoop can process something within a few seconds, that all of a sudden opens up a very different possibilities, how you can basically utilize this data you've been storing to actually run your business. So I'll give you one particular example. We work with a client, with a customer, who's basically, I wouldn't name the names right now, but they basically, are working with merchandising and producing pricing, kind of fluctuating pricing for the products on the web. And they basically were doing it with a system that was done overnight. So they collect the web logs, they see what people are actually looking at, they see the warehouse and merchandise labels, and they overnight produce new pricing for the next day. It was the only way to do it because they were doing it with Hadoop, and Hadoop takes hours and hours to produce this numbers for them. They were trying to basically move in a model where they can actually change the pricing as you browse a certain website based on your immediate behavior. And that's obviously was a very complex problem because although maybe mathematics are the same behind modeling, the performance requirements are completely different. Nobody's going to wait for 2 minutes while you're browsing. It has to be within a second or two while you're on the page before you clicked away. And they actually were able to get to this point with a lot of in-memory usage. They moved a lot of data in memory. They used combination of the Hadoop Accelerator and our core products, in our data fabric. And that's the good use case. And that's what we're going to be seeing more and more and more, that people will be moving to the use case and essentially applications where data stored in Hadoop will be used in a very operational, sub-second SLA use cases.
Well, it makes me think that I better get my own cluster running so I can browse with my own smart Hadoop cluster behind me telling me what to click on to get the best price.
Yeah, you can game the system. Yes.
Back on my side of the house, right? If they're going to game me. No, that's great. So, let's. I've asked enough questions here. There are a few questions coming in from the audience. Let me check some of those out here. So one question here is, I thought that data in memory would be lost in the case of a power outage. Is that not the case? And I guess that goes back to our discussion of data protection. And maybe it's because we walked a little bit fast through what grid means here. Maybe you could just cover that.
Yeah, so it's a very good question. It's literally one of the first questions we hear from kind of the clients that come to us and don't know much about in-memory computing. Essentially, when we talk about in-memory computing, the way I answer this is this. When we talk about in-memory computing, we typically talk about memory-first approach versus disk-first. And memory computing doesn't mean disk-less. Almost every system that we've seen our customers using disks, but it uses disk for the backup, for persistent storage. So essentially, what in-memory computing systems do very well and very smart, they allow you to transact and process data mostly in memory. And in the background, we're constantly backing up this data to a persistent disk, or a flash, by the way. We do it without much of a performance impact. So you still get all the benefits of the memory computing, performance and scalability. But in case of, a crash, or obviously if only one server crashes, we have the backups elsewhere in memory. But if you have, for example, a data center disaster, we have means to recover from that, either by storing things on disk locally or have, a data center application. So systems like GridGain has very sophisticated means to protect your data. So short answer is no. It's entirely up to you how you want to configure it. If you want to have it be protected, we have all the means to do that.
All right, here's a sort of a question going in a similar direction. Somebody's heard us talking about some machine learning and things and said, okay, so machine learning and more HPC-like apps don't always do well in Hadoop. Can this, I assume talking about GridGain, fold those workloads into the picture as well? So I'm assuming they're talking about things where, instead of having a highly parallelizable, man, I struggle with that every time, application that I can MapReduce on, that in some way, in machine learning and some of those HPC-like apps have a lot of intercommunication, high level of cross-node communication. So does GridGain help with those kind of workloads as well?
an excellent question. And my honest to God answer is I do not know. And the reason that I'm saying this is because you have to try. And this is one of those questions that I learned over almost 2 decades that you can never get or give a generalized correct answer. Different types of payloads, different types of algorithms can be parallelized very differently. Some of them what I call embeddedly parallel. You can parallelize them immediately, like a typical Monte Carlo simulation, for example. You can run Monte Carlo simulation for 1,000 computers with a linear scalability. There are different algorithms, like a linear algebra, that has very, hard parallelization and don't really parallelize well. And there's plenty of other, use cases where, every iteration uses a lot of data or data is not, collocated properly and on and on and on. It's a very technical conversation. So general answer, yes, GridGain has all the abilities and all the functionality that you can use to, make the, your algorithm as parallelizable as possible. But it's not about GridGain. GridGain just basically implements the very basic patterns that, known to academia, kind of entity processing, massive multiplayer, MPI-based, map reviews, RPC, all those different paradigms. Whether they fit your specific algorithm, only you would know. And that's how I answer all my customers. I will never make any generalized statements there.
So I guess that brings us, actually, I'll give you this one last question that's pretty relevant here. So can I download this from your website? Is there an easy way to tell exactly how much speed up we're receiving from this, I assume, when you turn it on?
Yes, we actually do have the whole set of benchmark, which is another open source project called, you can download from GridGain. It's called GridGain Yardstick. It's an open source benchmark tool, and you can just run it. You can modify it for your specific use case and see. So typically, I can probably say within the 2 or 3 days, you can get a pretty good sense of how much of speed up you're going to get, whether you use, our, GridGain Data Fabric or specifically Hadoop Accelerator.
All right. Okay. So I think that's actually just right on time here. I thank you so much for coming and talking to us today, Nikita.
No problem. Thank you, guys.
Thanks. And I'm sure we could do more of these and go into some more details on some very technical areas in the future. For the audience, if you're looking for more analysis of this particular in-memory opportunity for Hadoop, we do have our Tenasia Group report written up on this. Memory is the hidden secret to success with big data, and a focus on GridGain's in-memory Hadoop Accelerator with some of this context written out for discussion. And of course, I'll give you a plug here. More information, of course, can be found on this topic and your broader platform solutions on your website at gridgain.com. Thank you, guys. If there are any other comments or feedback that you'd care to send, feel free to connect with me directly at mikematch@tenasiagroup.com or hit me up at Small World Big Data. Thank you very much.
Thank you, Mike. Thank you, everybody.